Today I'll be deriving the energy slash work formula. Namely, it's this, that force times distance equals 1/2 mvf squared minus 1/2 mvi squared. Alright, and this equals work. Alright, so let's assume that the force is constant. If we assume that, then Fd would just equal MAD. And if the force is constant, then mass and acceleration, or let's also assume the mass and acceleration are constant. The acceleration also equals something else. Or we have the kinematics equations that V final equals V initial plus AT, and that D equals V initial times T plus 1/2 AT squared. Alright? Now, I want to rearrange this kinematic equation right here so I can isolate A. So I get this. A equals Vf minus Vi over time. Vf minus Vi over time. And then, look, Fd equals MAD, right? And MAD also equals times A. So Vf minus Vi over T. I'm plugging this A into this A and times D. So multiplying this, 1/2, this is a plus sign by the way, 1/2 AT squared. Alright, so we get that force times distance equals M, and I'm gonna factor out a T here. So we get this, Vf minus Vi, and I'm gonna factor out the T from here, so 1 over T times T, I factored out the T, so Vi plus 1/2 AT. These T's just cancel out, so we get that Fd equals mVf minus Vi times Vi plus 1/2 AT. And let me rearrange this equation right here again. AT equals Vf minus Vi, right? So I'm going to plug this AT back into here. So here's what I get. Fd equals mVf minus Vi times Vi plus 1/2 Vf minus Vi. Further simplifying down, we get Fd equals mVf minus Vi, and I distribute, I cancel out, so Vi minus 1/2 Vi is just 1/2 Vi, and plus 1/2 Vf. And then I'm gonna, distribute everything, so Fd equals 1/2 Vi Vf minus 1/2 Vi Vf plus 1/2 Vf squared minus 1/2 Vi squared. Alright? And look, these just cancel out. So we get that Fd equals, and I'm going to distribute the m to remaining terms here. So we get this, 1/2 mVf squared minus 1/2 mVi squared. And hence I derived the energy formula from the force times equal mass times acceleration formula. But what if the force is changing? So let's say we have this type of graph. We know if the force stays constant, this stays true. But what if the force is like constantly varying? So we have a force times or force distance graph, and let's say it goes something like this. The force is constantly varying. Well, what we can do is, like when we take an integral, we can find what this function equals. We can say f is a function of d, and we can just simply take an integral of this with respect to d, or dd, and then we get energy. So basically when we take an integral, we separate these into multiple rectangles, right? and these rectangles are like infinitely small. But I want you to notice something. These rectangles, each of these rectangles, assume an equal force. And this gets more accurate the smaller the rectangles are. So each rectangle assumes a constant force. So each of these rectangles would follow this formula. We know for certain. So we just get something like F, or let me think here. So we just get F1 D1, the first rectangle, plus the second rectangle, plus the third rectangle, dot, dot, dot. And this would all equal, well, it would equal 1/2 m2 v2 squared minus 1/2 m, where? We don't need a 1 there. 1/2 m1 squared. That would represent the first rectangle. Plus, and this second rectangle would have an energy value of 1/2 mv3 squared minus 1/2 mv2 squared. Because this energy thing starts off where this is ended. It starts where this is left off. So hence these would all just cancel out with each other. So this would cancel out with that, and we just get that the sum of the force times the distances just equals 1/2 m vf squared minus 1/2 m v initial squared. All right. Or this is not exactly true, but the integral of force with respect to distance should equal this. And like I said, it's basically, this is because of the nature of the integral. So if force is varying, then this formula does not work. However, it would work if we take an integral, because an integral assumes like multiple rectangles, and each of these rectangles assume there's a constant force. And the more rectangles there are, the more accurate we are. So if each rectangle assumes a constant force, then each rectangle would follow this formula. So we can just sum all the FDs, and we still get our remaining answer. I hope that made sense. All right, thank you.